If you've been following the world of autonomous vehicles, the last few years haven't just been about small improvements. It's been a total, almost nuclear re-engineering of the AI itself.
That's a good way to put it.
We've been watching this, frankly, audacious shift away from programming a car with, hundreds of thousands of lines of explicit rules to,
Yeah?
well, to teaching it how to drive like a human child.
Yeah, moving from a complex instruction manual to just learning by watching.
It's a huge leap. So today we're doing a deep dive into that very transformation within Tesla's full self-driving software. We're going to zero in on the big versions, V12 and the latest V14.
And our mission here is to really unpack this. Unpack the shift to an end-to-end neural network. Look at the consequences of relying only on cameras. That's the controversial Tesla vision strategy. And figure out what the newest updates really mean for you, the person in the driver's seat.
What's so compelling to me is this core conflict, this almost philosophical debate. You've got the pursuit of true autonomy using a minimalist sensor suite. I mean, Tesla is betting the entire farm on vision, which is a path that's just radically different from everyone else. You look at Waymo, which is just covered in LiDAR, or Mercedes with all their sensor redundancy.
It's a huge gamble.
So as we dive in, let's start right there with that seismic shift that began with V12. On a technical level, what is the fundamental difference between that old stack V11 and earlier and this new end-to-end AI approach?
Well, the defining difference is something engineers call the collapse of the control stack. And it's massive. The old way, the V11 way, was a classic modular software structure.
Okay, so break that down for us. What made that old stack, such an engineering nightmare?
Think of it like an impossibly complex flowchart. A multi-layered one, all written in C++. And we are talking about a lot of code.
How much is a lot?
The numbers cited are over 300,000 lines of C++ code, and that's just for planning and control.
300,000, just for that one part.
Just for that. And this massive code base had all these detailed, explicit planning modules, things that were constantly evaluating hundreds of potential paths every single second. It used all these well-known algorithms like A-star or RRTs to decide the path, all governed by these complex cost functions.
So the car wasn't just driving, it was running a nonstop, real-time simulation based on a bunch of math rules.
Exactly. Every single possible scenario needed an explicit rule. How fast do you take a curve? Well, that's a speed constraint function. What do you do at a yellow light?
All right.
That needs to check your speed, your distance, your braking ability, and then it has to choose between an accelerate rule or a brake rule.
And if there's a cone in the road?
Same thing. The planning module has to first identify the cone, then it calculates a safe bypass distance, then it adjusts the trajectory by, say, X meters, all while making sure it doesn't break some other safety rule.
The problem, as you said earlier, is that driving scenarios just cadeness.
Yeah.
They multiply exponentially.
They do. The moment an engineer solved one weird edge case with, 50 lines of custom C++ code, they would inevitably create 3 new, completely unintended problems somewhere else in that 300,000-line architecture.
Yeah.
The whole thing just became brittle and overly defensive.
And that explains the robot driver feeling, right? The hesitation, the jerkiness. It was the system just struggling to process all these competing rules in real time.
Precisely. The rigidity of that C++ structure meant the driving was often step function based. It would detect something, plan a response, execute it, stop, redetect, replan, re-execute.
It was a loop.
A very jerky loop. And crucially, the system would just freeze up when it saw something it hadn't been explicitly coded for. That's when the human had to take over. Okay, so then V12 comes along and introduces this fundamental change, the end-to-end neural network. How does that just bypass all that complexity? It's a completely different paradigm. It just throws out those intermediate planning and perception modules. It gets rid of them. So instead of programming how to drive, the system is just trained on enormous data sets showing what good human driving looks like.
So the input is just the raw camera feed, raw camera data in, and the output is the direct control signal, steering angle, accelerator position, and braking force. That is a huge philosophical leap. So instead of explicit code saying, if cone detected, adjust trajectory, the AI has just watched millions of videos of humans subtly steering around cones, and it incorporates that move into its own neural weights.
That is the core genius, or depending on who you ask, the madness of the shift. This network is trained on a data set of millions upon millions of miles of actual human driving, all gathered from the global Tesla fleet.
The data pipeline must be gargantuan.
It is. Reports suggest they're processing something like 400,000 video clips per second, and they use what's called shadow mode, which is key. The AI makes driving decisions but doesn't act on them. It just compares its choice to what the human driver actually did.
So if the AI is right, it reinforces the model.
Yep. And if the human has to intervene or takes a better path, that intervention becomes a super valuable labeled training example. That's how the network learns nuance, not rigid rules.
So what was the measurable impact on the code base? You called it a shocking reduction?
The reduction was astounding. That 300,000 plus lines of complex C++ plus planning and control logic, it collapsed. It went down to only about 2,000 to 3,000 lines of code.
2,000, that's orders of magnitude less complex. What could those remaining 2,000 lines possibly do?
They're the foundation, the absolute minimum set of instructions you need to just initialize, manage, and monitor the neural network model itself.
Okay, so they handle system safety, error reporting.
Exactly. And interfacing with the car's low-level control units and just ensuring the neural net's outputs are within basic physical limits, like making sure the car doesn't try to steer past its maximum lock angle. But the decision-making, the planning, the path prediction, that is all outsourced to the neurons now.
Which lets engineers focus on the training data, not debugging flowcharts.
That's the idea. Okay, so the technical debt is slashed. The car is learning intuitively. This gets us to the big promise. What does this actually feel like when you're in the car? What is this human-like driving? The promise is simple. Seamless fluidity and high confidence. And you need both of those for driver acceptance. Early reports from drivers who first got V12 were, well, they were immediate. They highlighted a dramatic change.
The nervousness was gone.
The nervous, tentative, jerky movements that really defined the V11 era, they were noticeably minimized.
I think anyone who used the old FSD knows that feeling. The car coming to a full stop before making an unprotected left turn, even when there's a huge gap in traffic, or that little unnecessary tap on the brake on a gentle curve.
That rigidity is largely gone. And it's because the end-to-end model operates probabilistically, not deterministically. The old system's cost function might see 10 options and pick the mathematically safest one, which was usually the most conservative.
The most robotic one.
Right. The new system, it interpolates, it shows a much more natural flow, it anticipates slowdowns more gracefully, blending the brakes and acceleration instead of just stepping on them. It repositions itself in a lane more subtly.
It drives like a person, a skilled, confident person.
Not a computer just following absolute rules. And that smoothness is the single biggest key to getting people to trust the system for more than a few minutes at a time.
That makes total sense. If the AI drives predictably, you can relax.
Yeah.
If it's jerky, you're always on edge, your foot hovering over the brake.
Okay, so let's pivot from the software to the core strategy that enables all of this. The commitment to vision only, the Tesla vision approach. This really is the strategic gamble that defines their whole effort and separates them from the pack. This is where the debate gets really heated. If you look at the history, Tesla's hardware journey has been a steady march towards sensor minimalism.
Right, back in 2014 with Hardware 1, they had everything.
Everything. Cameras, forward-facing radar, ultrasonic sensors, and they were using Mobileye's chip. Then with HW2 and 2.5, they added more cameras and switched to NVIDIA. HW3 in 2019 brought in their own custom, powerful FSD chip.
But the really big strategic pivot, the great sensor removal, that started around 2021, didn't it?
Indeed. That's when they made the pivotal decision to start eliminating forward-facing radar from most new Model 3 and Model Y vehicles, marketing it as Pure Vision Autopilot.
That was the first big step away from redundancy.
It was. And then in 2022, they announced they were removing the ultrasonic sensors, the USS, which were used for parking and proximity sensing. That signaled a full all-in commitment to a camera-only system.
But that decision drew immediate fire. I mean, you're depriving the system of a direct, physical way to measure distance.
Yeah.
What were the tangible, immediate consequences of ripping out radar and USS?
Well, the immediate transition was undeniably painful. It led to a lot of user frustration. There was a Washington Post report in early 2023 that highlighted the result. It said there was an uptick in crashes, near misses, and other embarrassing mistakes by Tesla vehicles, suddenly deprived of a critical sensor.
Functionality was reduced, too.
Temporarily, yes. Features like auto steer had their max speeds limited, and things like Smart Summon, which really relies on precise proximity sensing, were either disabled or just worked terribly. Okay, so this is the point where I have to ask. If the data right away showed an increase in mistakes when you took away a sensor like radar, doesn't that fundamentally undermine the whole safety case for a vision-only approach? That is the core high-stakes question.
Why take that risk when your competitors, like Waymo, are deploying these incredibly robust, redundant systems with expensive LiDAR. Or Mercedes is using a belt and suspenders approach with high-def radar.
Tesla's counterargument is basically twofold. First, they argue that LiDAR and high-def radar, while they're very precise, they're creating a world model that's separate from how a human perceives the world. That requires complex sensor fusion algorithms, which can be fragile.
And the second part. The second and more important part is their core belief. Humans drive safely using only their eyes' vision, therefore a highly trained neural network with 360-degree vision and faster than human processing should be able to do the same and eventually do it better. So they're betting that a massive investment in AI training can just overcome the physical limitations of the sensor suite.
It's an immense computational challenge. They have to achieve perfect three-dimensional consistency in their world model, purely from two-dimensional camera input, which puts immense pressure on two things: the quality of the cameras and the computational hardware you need to run these incredibly sophisticated neural nets. And that brings us right to the latest generation, Hardware 4. The demand for processing power is the limiting factor here. The end-to-end AI is computationally hungry. And while you need at least HW3 to run it, HW4, which started shipping in some vehicles in early 2023, is the platform that's really designed for the future software. It represents a massive leap in raw perception.
Let's get into the specs. What are the key upgrades from HW3 to HW4?
The camera system is the most obvious one. HW3 uses 1.2 megapixel cameras. HW4 uses high-resolution 5 megapixel cameras.
That's more than a four-fold increase in pixel count.
Which gives the neural network significantly richer visual data to train on and to infer from. This high fidelity is crucial for seeing small, distant objects like road debris or being able to read complex signs from further away.
More pixels, better input, better world model for the AI. What about those distinctive red-tinted lenses we've seen?
The red tint is a very deliberate optical choice. Those lenses are designed to reduce chromatic aberration and improve overall performance in low-light and high-contrast situations. You know, the classic Achilles heels for camera-only systems.
So improving night and twilight performance is vital if you're ever going to get to generalized autonomy.
Absolutely. You can't just rely on perfect daytime vision.
And on the compute side, the processing power is also a big step up.
A huge step up. HW4 features their custom FSD2 chip, which has 20 cores. Compare that to HW3's FSD1 chip, which ran on 12 cores. This just provides the necessary headroom for the ever-growing complexity of future neural nets.
I remember the HW4 rollout was a bit confusing for people. The hardware was in the cars, but the software couldn't fully use it right away.
That's a critical detail for anyone following this. When HW4 first shipped in 2023, the FSD software stack hadn't been optimized for that massive increase in camera resolution and the new chip. So initially, the software had to emulate the older HW3 setup.
Meaning it was actually downsizing those new 5-megapixel images.
Downsizing them back to 1.2 megapixels just to be compatible with the existing vision pipeline. It wasn't until a later software release, FSD v14.2.1, that the system could finally use the native high resolution of the entire HW4 camera suite.
It really highlights how difficult it is to configure that low-level software to manage such a massive data pipeline.
It's a huge challenge.
And beyond the driving, the jump to HW4 introduced some very real day-to-day complexity for owners, especially with how the car manages its own internal power.
Yes, this is a fascinating example of how more computational power changes everything. The HW4 chip and its components pull significantly more power, especially when the car is just waking up or starting. This higher electrical demand led to some really unexpected issues with external accessories.
You mean simple things? Like charging your phone or using a flash drive for Sentry mode?
Exactly that. Think about a basic USB hub in the glove box. Essential for Sentry video, charging, controllers, whatever. Accessories that were designed for the lower power draw of HW3 often struggled.
So when the HW4 car powered on,
when the FSD2 chip started spinning up, it demanded so much power that it sometimes couldn't allocate enough current to the external USB devices fast enough. That led to the car just not recognizing the device or intermittent power.
So third-party accessory makers had to completely redesign their stuff just to handle the car's power needs.
They did. We saw manufacturers having to implement these sophisticated power load management protocols. So instead of just instantly drawing max power, which the car system might reject, the new hubs had to do a gradual step-by-step power-up to make sure they were recognized after the car's main systems booted up.
It's a really good example of the hidden complexities of this kind of cutting-edge tech.
It really is.
Now, While the focus is always on the new hardware, it is worth noting that Tesla seems committed to keeping the legacy fleet going. They're still pushing some visualization improvements to older Intel-based cars, right?
They're showing that commitment, which is important for the millions of early adopters.
Yeah.
While you need the high-power AMD Ryzen systems for most of the really sophisticated continuous visualizations, Tesla has extended certain FSD elements, specifically the high-fidelity vector view, to the older Intel-based cars, especially when the car is in reverse.
It's a small detail, but it shows the older cars are still benefiting from the improved perception model.
And it provides a more consistent user experience, which is key. Okay, let's move into the latest software releases, FSD v14 and v14.2. This feels like where the training wheels start to come off for the end-to-end network, as it starts tackling the trickiest real-world scenarios. v14.2 really embodies a significant maturation of the model. The core improvement is in the vision encoder, which was upgraded to really leverage those higher resolution features from HW4 that we just talked about.
And that translates directly into better situational awareness.
Directly. Improved perception and classification of emergency vehicles, faster detection of small road debris, and better interpretation of subtle human gestures, like a pedestrian waving you on.
Handling emergency vehicles is so critical for safety and just, legality.
Yeah.
How did v14 specifically tackle that?
The key is explicit integration into the learned behavior. v14 added specific, targeted handling to make sure the vehicle pulls over or yields correctly for police cars, fire trucks, ambulances when their lights or sirens are active.
In the old system, that would have been a complicated, hard-coded set of rules.
Right. But in the v14 end-to-end system, this behavior is now integrated into the navigation and routing layer, which itself is now baked right into the vision neural network.
So the car isn't just reacting to flashing lights, it's integrating the whole situation into its long-term plan for the route.
Exactly. Navigation and routing aren't separate planning steps anymore. By integrating them into the visual network, the system can handle unexpected things. A major detour, a blocked road from an accident, in real time, relying purely on its visual world model. It doesn't need pre-map data. It can visually assess a detour and incorporate it into the driving decision with the same neural stack that's controlling the steering wheel.
What about those common, annoying scenarios that FSD used to struggle with? Road debris, confusing intersections, things that cause those hesitant moments.
v14 really aimed to polish those 90% scenarios. The update enhanced how it manages static barriers like traffic cones and dynamic gates, significantly improved handling of offsetting road debris, tires, tree branches, boxes, and it just generally refined complex low-speed maneuvers.
Like unprotected turns and vehicle cut-ins.
Unprotected turns, aggressive cut-ins, navigating around school buses. The underlying goal isn't just to complete the maneuver, but to do it reliably, so the car can recover smoothly without needing a human to take over every single time.
One of the most user-facing changes in v14 was the introduction of customized driving behaviors, the speed profiles. This feels like an acknowledgement that not every driver wants the same level of aggression.
Absolutely. v14.1.7 gave drivers powerful new tools for customization, moving beyond just chill and standard. They introduced Sloth and Mad Max.
Sloth and Mad Max. Sounds like the engineering team was having a little fun.
It does. Sloth is designed for maximum conservatism. It dictates lower speeds relative to the limit and picks lanes that minimize maneuvering. It's all about stability and comfort.
And then there's Mad Max,
which allows for substantially higher speeds and far more frequent assertive lane changes than even the old hurry setting. This gives you the ability to tell the car to be either a nervous Sunday driver or someone who is perpetually late for a flight.
So if I select Mad Max, what does that actually translate to? Is the car driving right up on someone's bumper before it merges?
It translates to assertiveness, which is a key part of confident human driving. On the highway, MMX will select gaps for merging that an average human might take, but which the old FSD, programmed for maximum safety margin, would have just passed up. It accelerates into gaps much more aggressively.
Okay, but there was a UI change that came with this that sparked some controversy, wasn't there?
There was. In previous versions, you could use the right scroll wheel on the steering wheel to set a very precise speed offset, say exactly 5 miles per hour over the limit. It gave you meticulous control.
And in v14.
That scroll wheel was repurposed. It now adjusts the speed profile setting itself.
So you lost the ability to set that precise, absolute speed margin that you might use for 95% of your driving.
Exactly. And while the new profiles were interesting, a lot of dedicated users complained that losing that precise speed offset felt like a massive downgrade. They felt the broader profiles didn't let them fine-tune the speed for specific routes, and it often led to unnecessary micro-braking because the profile's internal margin was too wide.
It's an interesting tension. The AI wants flexibility through broad profiles, but human drivers often crave precise, predictable control over speed.
It is.
Okay, beyond road driving, let's look at low-speed destination management. This is critical for that long-term robotaxi vision.
V14 introduced arrival options, which is a big move in that direction. When you navigate somewhere, you can now proactively select your preferred parking location, whether it's a specific parking lot, on the street, a driveway, a parking garage, or just curbside.
And it remembers your preference for next time.
It persists that preference, creating an intuitive default for future trips.
That's great for the high-level planning, but user feedback has consistently shown that the low-speed, detailed maneuvering for parking and summon, it's still way behind the high-speed highway competence.
That's the recurring theme, a distinct split in performance. Core driving, especially with V13 and now V14, is highly competent on major roads. But features that need high geometric precision at low speed like Advanced Summon or ASS are still often described by users as basically unusable for reliable operation.
They're slow, they get confused.
And they require frequent human babysitting. Parking and emergency features are getting a lot of focus in the updates, but until that low-speed geometric precision is solved, the dream of summoning your car across a busy parking lot is still pretty far off.
And this brings us right back to the technical trade-offs of the vision-only system. Whenever the AI misinterprets visual data, we see the return of these phantom issues, and V14 had reports of these problems coming back.
It's a serious vulnerability. Despite adding that dedicated emergency vehicle handling, V14 saw some disconcerting reports of false positives. Users noted the car would randomly detect a phantom siren that wasn't there and proactively pull over and stop, which is, disruptive and confusing.
And even more seriously, phantom braking.
Some users reported the return of phantom braking, that sudden, jarring braking event when the car incorrectly identifies a shadow or a change in road texture as a stationary obstacle.
Okay, we need to challenge the premise here for a second. If V12 successfully reduced phantom braking by getting rid of that brittle rules-based system, why would V14, built on the same end-to-end architecture, reintroduce such a fundamental safety flaw?
It's a great question.
Doesn't that suggest that even this human-like learning is still fundamentally unreliable, or maybe just too sensitive to subtle data changes?
It raises serious questions about the generalization and stability of the neural network. When a new version is released, especially an early access build like V14, the developers are often focused on adding new complex scenarios like debris or emergency vehicles.
And training on that new specific data can mess with the older, more general learning.
It can sometimes destabilize it, causing a regression in a basic area like phantom braking. It's a very delicate balancing act. They're constantly expanding the AI's capabilities, but every expansion risks introducing unexpected noise that can lead to these critical false positives. It just underscores the immense pressure on their validation and retraining loops.
To make sure that adding new intelligence doesn't compromise foundational safety.
Exactly. It ties right back to the difficulty of creating that perfect 3D world model using only 2D cameras. Any transient visual noise, a reflection, confusing light, can be misinterpreted as a solid object and trigger a phantom reaction. And this need to interpret 3 dimensions perfectly from 2 dimensions leads us directly to our final and maybe most fascinating technical section. The visualization paradox.
The visualization paradox is one of the biggest disconnects for the casual user. After V12, the highly detailed, beautiful graphics on the screen, they no longer directly control the car. They're just running in parallel.
This is so crucial to understand. Before V12, the visualization was a direct, literal representation of the car's planning stack. It showed you the output of the object detection modules, which were then explicitly fed into the planning modules.
So if it saw a pedestrian icon, it would plan around it.
Right. Post V12, the end-to-end neural network operates in a high-dimensional space. It takes in raw pixels and outputs raw commands. It completely bypasses the creation of many of those explicit labeled objects you see on screen for its actual driving decisions.
So the visualization is basically just an expensive secondary process running on a different chip.
In many cases, yes. The vehicle controls come from the massive neural network on the dedicated autopilot computer, which is optimized for super low latency. The visualization you see, the rendering of the cars, the pedestrians, that's running on the separate consumer-facing infotainment computer's GPU.
And it's primarily designed to just render a simplified version of what the underlying Tesla vision system perceives.
Rather than acting as the actual input for the FSD control network.
So what's the definitive proof we have that the car is driving based on the deep neural output and not the graphics on the screen?
The evidence comes from user observation, and it's pretty compelling. For instance, the car will consistently and correctly obey physical objects like traffic cones or speed bumps, even in cases where those objects completely vanish from the on-screen visualization after the V12 transition.
Okay, so it sees things that aren't on the screen.
And conversely, and this is maybe more telling, FSD has been seen to ignore obvious false positives that are shown in the visualization. If a phantom pedestrian or a vehicle momentarily flashes on screen, the car often just drives right through the phantom image without reacting at all.
Proving the control stack didn't see it as a real threat.
Exactly.
So the visualization is really just a confidence-building tool. It's not a functional component of the decision-making.
Precisely. It serves the driver's need for confirmation. We are psychologically comforted by seeing that the AI recognizes complexity. If you see the car accurately modeling a specific type of semi-truck, it reassures you that the underlying system is sophisticated. As that visual accuracy improves, driver trust increases, even if that display isn't what's directly turning the steering wheel.
And speaking of improved visualization, the latest software updates show a massive investment in visual accuracy, moving way beyond generic shapes and boxes.
This is where the visualization team is really catching up to the AI's increased perception capabilities. Recent software versions are preparing for a major overhaul, adding a huge library of highly specific 3D assets to replace those generic objects.
Give me an example. What kind of detail are we talking about?
They are moving beyond just classifying a generic truck or person. The new asset library has highly specific renders for ambulances, fire trucks, distinct types of school buses, specific European semi-trucks, even subtle objects like strollers, trains, and trams.
So it can tell the difference between a person on a scooter versus a bicycle.
That's the goal. This granularity is possible because the powerful v14 neural network can now classify objects far beyond just broad categories. It can reliably differentiate between a generic box truck and a fire engine.
That's a necessary step toward building a detailed, human-readable world model. But you mentioned earlier that low-speed geometric maneuvering is the ultimate challenge, and that requires something even more precise than the current FSD visualization, which leads us to voxel grids.
Right. The voxel grid system, or the high-fidelity occupancy network, is fundamentally different from the visualizations we've been talking about. This technology, which is detailed in Tesla's patents, solves the problem of precise 3D geometry, and that is absolutely essential for low-speed navigation in tight spaces. Think about pulling into your cluttered garage.
How does a voxel grid differ from what the cameras are already doing with vision?
The FSD visualization we see now is based on identifying objects and then placing 3D models of those objects in space. The voxel grid, or volumetric pixels, doesn't really care about object classification at first. It divides the 3D space around the car into thousands of tiny millimeter-sized cubes, the voxels.
Okay. The AI's job is then purely geometric, to determine, with centimeter accuracy, whether each tiny cube of space is occupied by any physical material, or if it's empty space the car can safely drive through. So it's not looking for a box, it's just looking for occupied space.
Precisely. This approach bypasses the ambiguity you get with object classification and just focuses on safe movement geometry. This is fundamentally much, much harder to do with pure vision than it is with LiDAR, which physically measures distance with light. Tesla has to train its network to infer depth and shape perfectly from 2D input.
Have we actually seen this technology deployed in consumer cars yet?
We have, but in a very limited way. This system is what powers the high-fidelity park assist feature, and that's only available on newer vehicles, the ones with the AMD Ryzen infotainment systems, and only at very low speeds, typically under 6 miles per hour.
So this is the prerequisite technology for things like a reliable advanced summon.
Reliable summon and the desired banish function, which would let the car precisely move itself out of the way on command. This creates a real technical split then. You have the abstract, fast-moving FSD visualization for high-speed driving, and this precise, geometrically accurate, voxel-based visualization for low-speed maneuvering. That is the current reality. The end-to-end network excels at the predictive, probabilistic task of driving like a human at speed. The high-fidelity occupancy network solves for the centimeter-accurate, deterministic task of navigating cluttered 3D space at low speeds. The patent suggests that this voxel-based approach might eventually replace the current, cleaner FSD visualizations entirely.
Why would they do that? Why replace the clean graphics with something that sounds so much more geometrically complex?
To maximize trust. The ultimate goal is to give you a visualization that mirrors the geometric world the car truly perceives. If you, the driver, see the car modeling every tiny curb, every trash can, every protrusion with perfect fidelity using voxels, it provides maximum assurance that the car understands the actual physical space it's in.
So it's a shift from showing the driver what the car sees in terms of labeled objects to showing the driver how the car perceives physical space for safe movement.
Exactly. And merging these two competencies, high-speed confidence and low-speed geometric precision, that is the final great hurdle before true unsupervised autonomy is even viable.
This deep dive has given us an incredible look at the guts of this revolution. Let's try to recap the critical takeaways from this transformation, focusing on the trade-offs of this vision-only bet.
Okay. First, the move to end-to-end AI with V12 was the single biggest architecture change. It dissolved hundreds of thousands of lines of brittle C++ code into a neural network trained on human driving. The result is dramatically more fluid, human-like driving.
Second, that vision-only strategy, while it forces the AI to develop this incredible visual intelligence, is also the source of recurring instability. Ripping out radar and USS increased reliance on the AI to infer depth, which led to those initial crashes, limited features, and the continued frustrating return of phantom braking and false positives in newer versions like v14.
Third, hardware evolution is absolutely crucial. HW4 significantly boosts capability with 5-megapixel cameras and the 20-core FSD2 chip, but that hardware required months of software catch-up before its full resolution could even be used.
And finally, the v14 updates refine the system, adding detailed control through features like the Sloth and Mad Max profiles and better destination management. And crucially, we learned that the complex on-screen visualization is a separate process used solely to build driver confidence, a purpose that's about to be enhanced by new, highly specific 3D models and those geometrically precise voxel grids for low-speed tasks. This whole journey raises one final provocative thought for you to consider. We keep investing so heavily in visualization because it is, right now, the driver's necessary supervisor. It's our window into the car's world model. But the ultimate goal, robotaxi confidence, requires the car's internal world model to be utterly infallible. So if true unsupervised autonomy means the driver doesn't need to look at the screen or intervene, what would it take in terms of data, processing power like a future HW5 or AI6 and AI stability, to guarantee the car's internal perception is so perfect that you, the driver, no longer need the reassurance of those graphics to feel absolutely confident in the machine's judgment?
If the machine truly sees perfectly, the visualization becomes redundant, yet the investment in visualization fidelity is surging.
That surge suggests the technical and, probably more importantly, the psychological trust gap is still vast.
Closing it requires not just incremental improvements, but reaching a level of predictive intelligence that can handle every obscure edge case instantly and reliably. And that level of competence, as some analysts suggest, might still be years and several hardware generations away.
A phenomenal technical challenge, and a battle of sensor philosophy that continues to define the future of the autonomous road. Thanks for joining us for this deep dive into the vision-only revolution.
My pleasure.